Hello and welcome to the vapor pressure notes. Vapor pressure is defined as the pressure of a gas right above a liquid. So something that we consider a vapor is usually something that's typically considered a liquid at or typically found as a liquid at room temperature, but can be vaporized with the addition of heat. Water is an excellent example of this. So if you think about if you have some liquid water and you apply heat to it and you get steam, kind of that moist steam is what we think of as being a vapor. Vapor pressure has some similarities with, or vapor behavior, I should say, has some similarities with regular old gas behavior. Keep in mind that when we talk about pressure, we are talking about, pressure is referring to collisions of gas particles with the sides of a container. When we talk about something that's not really contained in a container, it could just be like anything in the room. For example, air pressure is determined as, those molecules hitting you, the desk, the wall, etc. So pressure relates to the number of gas particles in a sample. If you look at these two diagrams that I have right here, the pressure will be higher in the container that has more molecules. So the more gaseous molecules you have, the higher the pressure. More particles in a vapor, more collisions with the container, higher vapor pressure. Fewer particles in a vapor, fewer collisions, lower vapor pressure. So vapor pressure is going to tie into how easily something actually vaporizes or becomes a gas. It's also going to tie into temperature. So if we look at this little bottle that I drew right here, initially we have 4 samples in the gaseous phase. Imagine I just threw a little fire under there. Not really a great example, not really a great thing to do with a closed container, but we would see some of these liquid molecules going into the gaseous state. We now have 1, 2, 3, 4, 5, 6, 7, 8 gas particles. So we would have now we'd have more gas particles. In this case, we now have 8 of them in my picture. And what that's going to do, we're going to have more particles colliding with the side of the container. So this is going to increase my vapor pressure, or just, the general pressure inside of that container. There are 3 substances that we're going to do a demo in class with that you can see, how quickly they evaporate. You'll also be able to look at these on reference table H and that will help you determine if they're what their vapor pressures are and compare their intermolecular forces. So keep in mind that intermolecular forces are forces between molecules. If we compare these 3 substances, propanone has a very low boiling point, okay? It's very easy to get the molecules to be separated from one another because the forces in between them are weak. On the other hand, if we contrast that to water, which has a much higher boiling point, water has strong intermolecular forces. It's much more difficult to get it to become a gas. Ethanol kind of falls right in the middle. So if something has weak intermolecular forces, you imagine you put all these containers at the same temperature. Something with weak intermolecular forces is going to have a lot of vapor molecules. It very easily becomes a gas. Ethanol, on the other hand, so, the propanone, we have a lot of the particles becoming a gas. In ethanol, we have these moderate intermolecular forces. Actually, let's just keep it like that. So we're going to have some particles becoming a gas, not quite as many. When we look at our water sample, it's actually relatively difficult for water to become a gas. Because it's more difficult, we're therefore going to have comparatively few particles in the gaseous stage. So because we have less particles becoming a gas, therefore, we're going to have lower vapor pressure. So what this means is when we have weak intermolecular forces, lots of particles, high vapor pressure. When we have strong intermolecular forces, we're going to have fewer particles and therefore a lower vapor pressure. We can also use this to talk in terms of boiling point. An alternative definition for boiling point is the temperature at which atmospheric pressure is equal to vapor pressure. So when something boils, what actually has to happen is the vapor pressure of that liquid has to become equal to the atmospheric pressure. If you have a sample of water being held at 75 degrees Celsius, its vapor pressure is 40 kilopascals. The atmospheric pressure is 101.3 kilopascals in a typical room like our classroom. Not the greatest scientific explanation of this, but I really like kind of thinking about this as little like force arrows. So the atmospheric pressure is higher. It is pushing down on the surface and keeping the water a liquid. That vapor pressure of water, not quite enough to overcome that. So it's not really the greatest scientific explanation, but I just like to think, hey, the atmosphere is pushing down more than that water is pushing up. So if we think of vapor pressure as the pressure of the liquid wanting to escape, we just don't have enough force to really overcome that current atmospheric pressure. However, as we increase temperature on a sample, its vapor pressure increases. So if we heat water up, we can actually heat it up to where its vapor pressure is equal to the atmospheric pressure. Now that we've actually increased this so that its vapor pressure is equal to the atmospheric pressure, we will now have boiling occur. So in other words, if we get our atmospheric pressure and our vapor pressure equal, boiling will occur. So check out reference table H. There are some things I'm going to have you kind of do to mess with this reference table a little bit. Because vapor pressure and boiling point, because boiling point is where vapor pressure and atmospheric pressure are equal. Sometimes I just like to write atmospheric pressure for ATM over here, just to remind me that they can be used kind of interchangeably if I'm determining boiling point. Temperature could be a boiling point. So that just kind of helps you with the way some of these questions are worded. Also, please notice your x-axis goes by 5s, your y-axis goes by 10. That can be confusing. Another thing to add, something that has a very high boiling point is going to have a lower vapor pressure. That tells you you have strong intermolecular forces, higher vapor pressure, lower boiling point, weak intermolecular forces. So these are actually ranked on this table by their intermolecular forces. So the strongest intermolecular forces on the table are ethanoic acid. If we want to determine something's boiling point, water is going to boil, if we want to determine what temperature water will boil at 80 kilopascals. We find 80 on our x-axis, so 50, 60, 70, 80 is right here. Remember those by tons. And remember, that's where our atmospheric pressure and our vapor pressure will be equal. So I can then follow that over to the line for water. So follow it way over here. And then I simply have to follow it down. And it hits right under, remember this is by 5, so it's kind of like right under 95. I'd say about 93 to 94 degrees Celsius. What's that dotted line all about? Great question. So that dotted line is at 101.3 kPas. That's what we know as standard pressure. I don't care if you write that on your table or not, totally up to you. So that's going to be our standard pressure. And if you follow that over for water, so if you follow that dotted line over to where it hits water and you read the temperature that that happens at, that is happening at 100 degrees Celsius. This is going to tell us something called the normal boiling point, or the boiling point at standard pressure. So you know that water boils at 100 degrees Celsius. That actually changes with atmospheric pressure. We're just pretty much always at about 101 kPa. If we want to determine the normal boiling point of propanone, we would use that same line, so using that same dotted line, figuring out where it hits propanone, following it down here. That's going to happen right about 55 or 56 degrees Celsius. So normal boiling point just means your pressure is 101.3 kPa. And just a couple side notes, a couple things that are interesting. If you look at the side of a cake mix box, you will see high altitude cooking instructions. This is because at high altitude, you have lower atmospheric pressure. Lower atmospheric pressure is going to cause you to have a change in the boiling point of water. So something will boil a little bit easier. Therefore, you don't have as much heat in the water when it boils. So that's going to affect how you cook something. Pressure cookers increase pressure, and this is going to increase the boiling point of water. Therefore, you have liquid water with more energy in it, and it can cook things faster. So a couple quick questions. You should be able to determine the normal boiling point for each substance on the chart. We already did water is 100 degrees Celsius. We did propanone is about 56 degrees Celsius. So we'll do ethanol and propanoic acid. So ethanol hits right here, which if we follow that down, it'd give that about 80. And ethanoic acid would give about maybe 118. You should be able to determine which substance has the strongest intermolecular forces. We already talked about that. Ethanoic acid. Lowest vapor pressures on the table, highest boiling point. For water to boil at 50 degrees Celsius, what would we need our atmospheric pressure to be? So we're going to find 50 degrees Celsius, right here. We're going to follow that up to our water line, which is right about here. It's very difficult to read this on the smartboard, but I'm thinking it's coming out right around 12. Remember that axis goes by tens, not fives. So that's going to happen at about 12 kPa. It's a pretty low atmospheric pressure. We'd probably all be dead. You can actually create low pressures. You can have a chamber that creates that. But you wouldn't want that to be your pressure in the room. If water does not begin to boil until a temperature of 110, what must the atmospheric pressure be? So we're going to go back to our table again. When water is boiling at 110, which would be right here, we're going to follow that up to our water line. It's right about there. So I'd say that's hitting at about probably 142 Celsius, or 142 kilopascals. So generally on this table, if they give you Celsius, read it for pressure. If they give you pressure, read it for Celsius. Vapor pressure water is very low at 0 degrees Celsius because water is a solid at 0 degrees Celsius. As the temperature of a substance increases, its blank increases. As you increase something's temperature, its vapor pressure will increase.